Here's the review for test 1. This will be on chapter 13 only. I have these problems up here. Let's go through some of them. I can at least get you started on them. Some of them we might finish. You can send me emails and come in the mornings on WebEx, please, and we'll discuss these some more before the test comes up. Here's the first one. Suppose I want to find the local linear approximation to a function of two variables. All right, in calculus 1, that meant you found L of x, the function that was the tangent line to the curve. F of xy here is the linearization, the local linear approximation, it's called both, is the tangent plane at the given point. So you have to be given a point along with the function. What does the tangent plane look like? If you just write the equation for the tangent plane, which is actually in the next section, I'll accept that. Or you can use what they officially call the local linearization, which is the tangent plane function. And here's how you compute that. You just have to look at this formula. The test will be open book, so it shouldn't be something you can't look up. Here's f of xy equals 1 over square root x squared plus y squared. In order to calculate the tangent plane, and I need this at the point 5, 12, in order to calculate the tangent plane, I need the partial derivative. So I'll calculate fx, the partial derivative with respect to x. Well, if this function I think of as x squared plus y squared to the minus 1/2, that's easier than using the quotient rule, right? Is to use just the chain rule like this. So let's write that as x squared plus y squared to the minus 1/2. Then the derivative, if I think of this as u to the minus 1/2, is partial of u to the minus 1/2 with respect to x, and now you choose the chain rule for that and say, oh, this is the ordinary derivative of u to the minus 1/2 with respect to u, partial of u with respect to x. Why do I make one of them a partial derivative and one of them an ordinary derivative? It's because u to the minus 1/2 is a function of only one variable u, so I write ordinary derivative. But u is a function of two variables, x and y, so I write a partial derivative. And so it's the usual chain rule, the u to the minus 1/2 du dx. It's just to write this one as a partial derivative because u is a function of more than one variable. If you don't get the notation right, I'll probably mark it on your paper, but I probably won't count off as long as you get the answer right. Derivative of u to the minus 1/2 is minus 1/2 u to the minus 3/2 du dx. Derivative of x squared plus y squared, here's u, is 2x plus 0, right? Now the 2 can cancel the 1/2, and I can put back, I now have minus x times u to the minus 3/2 is 1 over x squared plus y squared to the plus 3/2, right? 1 over u to the 3/2 is u to the minus 3/2. Now I have partial with respect to x. I have an equally difficult problem to take the partial of f with respect to y. Fortunately for me, this function that I'm given, right, 1 over square root x squared plus y squared, is completely symmetric in x and y, right? So if I interchange x and y, I get the same function. That means that the partial with respect to y is completely symmetric also. It must be minus y over x squared plus y squared to the 3/2. Because I just interchange x and y to get the partial derivative with respect to y, since the original function had that symmetry. Now, in particular, however, I don't need just the partial derivatives for the linearization. I need the partial derivatives at this point 5, 12. So let's say fx at 5, 12 is this function. Plug in 5 for x and 12 for y. I get minus 5 over the square root of, well, let's say 5 squared plus 5 squared plus 12 squared to the 3/2, right? But the square root of 5 squared plus 12 squared is 13, so I've got 13 cubed. So this is minus 5 over 13 cubed. Similarly, Fy, cut off the end, let me make that a little smaller. There we go. Fy at 512 gives me minus 12 over 13 cubed. So I have those two calculations, and now what I want is L of xy, and you just memorize this formula or you can look it up quickly at the time of the test. It has to be f at 512 plus partial with respect to x at 512 times x minus 5 plus partial of f with respect to y at 512 times y minus 12. And there it is, the linearization. Can you see all of that, hopefully? The linearization is this. Well, f of 512 is 1 over square root of 5 squared plus 12 squared is 1/13. And then this one we found out was minus, that's right, it's what, minus 5 over 13 cubed times x minus 5 minus 12 over 13 cubed times y minus 12. Alright, so let's see. I can write these all over 13 cubed by writing this one as 13 squared, or 169 over 13 cubed. And then I can write this whole thing, factoring out the 1 over 13 cubed, as 1 over 13 cubed times 169 minus 5 times x minus 5 minus 12 times x minus y minus 12. I'll let you go ahead and finish the algebra. I think that's all the interesting stuff that's there. Well, maybe I should finish this one. Alright, so this is 169 plus 25 plus 144 is 169, so that comes out to be 0. So I have 1 over 13 cubed times minus 5x minus 12y. And there's my local linearization, is this one right here. So hopefully we get the same thing. And then I'll make the additional note, if you did the tangent plane calculation instead, what would you get? You'd get z equals 1 over 13 cubed times minus 5x minus 12y. You can see that's a plane, right? If you rearrange it algebraically, you get ax plus by plus cz equals d. And in this case, d equals 0, so this is actually a plane through the origin. So there's a very interesting problem to start off. Let's take a look at the next one. It says this: use a total differential to estimate the change in the value of f from p to q. Compare your estimate with the actual change in f. Now actually what you can do for this f of xy, which is x plus y over x minus y, and you're interested in this going from p at minus 1, 2 to q at minus 1.02, 2.01 nearby. Technically what you can do is the tangent plane again. One of the interesting things about this early section is that when they do the local linearization, when they do the estimation by tangent plane, and when they do differentials, it all is just a tangent plane approximation in all of it. So if you use the local linearization at this point, now the tangent plane at this point, and then plug this point into the tangent plane, you get the right answer. It's all the same thing in different klutzy notation that's used actually in practice in lots of the sciences. So it's partly just getting you used to notation. I'll go ahead and do that. But if you use the tangent plane at this point and plug in this point, you get the same answer. This is 1.02 comma, so it looks like a 3 there, doesn't it? Now, that means I have to do the following. Here's the total differential. It's df equals df dx dx plus df dy dy for a function of two variables. It looks like the differential you did in calculus 1 a lot, right? In calculus 1, if f was a function of one variable, x, you put df, dx, and made this an ordinary derivative because of the derivative of a function of one variable. Here we do the same thing, df, dx, but now we have y, so we add df, dy, and this turns out to give you the tangent plane approximation to this function. And you're estimating the function at this point by finding the tangent plane at this point and plugging in these numbers to the tangent plane. It's this kind of a picture. I'd like you to understand what's going on pictorially, not just be able to calculate this, because when you go out in the workforce, you want to be able to understand what it is you're doing and why, right? And if you can picture it, Einstein said that imagination is more important than knowledge. How about that? And I think part of that is if you can picture things, you can imagine things, then you can figure out how to do these problems better than otherwise, than if you just have the knowledge, right? But this is the idea. You've got a tangent plane at P. So in the XYZ space, you go up to the point F at P, and you take the tangent plane here, and there's another point Q over here, and not drawn for these particular points. And there's an actual point on the function up here, and then there's a point in the tangent plane, and you're estimating this value. Here's the function z equals f of x, y. And so you're finding f at q. Instead of finding f at q, you're estimating f at q by taking L at q, the local linearization at q. But we're going to use this klutzy notation of the total differential. And I'll tell you that's actually a very important notation, because if you want to take differential geometry or topology or all those sorts of courses, they use this notation extensively. It's very important theoretical notation, even if it is just a tangent plane approximation again. So what's df dx? Now we have a difficult problem. If I calculate partial of f with respect to x, well, this is a quotient is the last operation. So we'll go to the quotient rule first, right? If I think of this as, well, we could do this by the Seven Dwarfs rule, right? If we call this high and this ho, right? And so, using this differential notation, what's the quotient rule? Ho d high minus high d ho over ho ho, right? And off to work we go. So if you have trouble with the quotient rule, like a lot of us do, there's an easy way. You can do it in a song or something. All right. So here's f, and we'll say more generally, partial of f with respect to x, when f is, let's do it this way, u over v is v u prime minus u v prime over v squared is the short way to do it. And so what is this? V is x minus y minus u prime, but really we should change this because we're taking partial with respect to x. We'll change this, call it v ux minus u vx over v squared, because it's partial derivatives. So it's the chain rule for partial derivatives. V ux, let's see, ux is 1 minus u, which is x plus y. Vx is 1 all over v squared, x minus y squared. And there's the partial derivative with respect to x. We can simplify because we have x minus x here. These cancel. Minus y minus another y is minus 2y over x minus y squared. So there's fx, or we can call it df dx. The notations mean the same thing, recall. And now we want to put it at 1, 2. So let's put df dx at the point, let's use the same notation as last time, 1, 2. Put in 1 for x and 2 for y. We've got 1 minus 2 squared is 1 on the bottom. And minus 2 times 2 is minus 4 on the top. This comes out to be minus 4 just by plugging in, right? Now, we also need df dy, also known as fy. And this would be v uy minus u vy over v squared by the quotient rule. And so v, let's see, is x minus y times partial of u with respect to y is 1 minus u, which is x plus y, times vy, which is, if you look up here, is minus 1, all over v squared, x minus y squared. And you know, I wrote this nice notation here. There is something implicit in here. This total differential is at the point P, so this is really partial derivative with respect to x at the point minus 1, 2. This is the other notation for the same thing we wrote last example. It means df dx plug in minus 1, 2. Plus df dy plug in minus 1, 2. So it has to be at the point P of tangency of the plane. So it's df dx dx plus df dy dy, but you have to plug in the numbers here. So these two are actually numbers, and then dx and dy are increments in x and y is what those are. Now, so I need not just df dy, but df dy at the point 1 minus 2. And so let's see, I've got to finish doing my calculation here. This time, minus y plus y, the y's cancel, and I get 2x over x minus y squared. At the point, so this is 2x over x minus y squared at the point 1 minus 2. So I'll plug in 1 for x, I get 2 on top over, again I get minus 1 squared on the bottom. This just comes out to be 2. So partial with respect to x, the f is minus 4. Partial with respect to y is plus 2. And now I bring down what I had up here. I'll say that df is df dx dx plus df dy dy. And sometimes we just sort of tacitly assume that you know these are evaluated at the point. But maybe I better put it in here. 1 minus 2, minus 1, 2, excuse me. And minus 1, 2 gives us, let's see, minus 4 dx plus 2 dy. So there is the total differential at the point minus 1, 2. All right. So now, what I want to do is estimate f at q. So f at q is approximated by df. Well, df is the change in x in f actually. So f at q is approximated by f at p plus df. I don't know if they quite use this notation in the book, but you take f at minus 1 plus 2 plus df was minus 4 dx plus 2 dy. That's how we actually estimate the function at the point. We add df, the estimated change in f. That's what this was up here. I should have maybe marked it. This little amount is df, and so you add it to the value of f at, it's not that. This is df. So delta f, the change in the function, is this amount, and we're estimating delta f, the change in the function going the z-coordinate going from this point to this point, by df, the change up to the tangent plane. So df is the height of the tangent plane above the original point, delta f is the height of the actual function you're estimating. So the exact change will be f of p plus delta f. The estimated change is f of p plus df. And now I have to put in f at minus 1, 2. Let's see, that's minus 1 plus 2 over minus 1 minus 2. That's f at minus 1, 2. And then I add to that minus 4 times dx is the change in x. So x went from minus 1 to minus 1.02. It changed by minus 0.02. Plus twice dy is the change in y. It went from 2 to 2.01, so its change was 0.01. Now we just have to do this calculation. Let's see, minus 1 over plus 1 over minus 3 is minus a third. And then I add to that 0.08, and I subtract, and I add to that to minus 0.333, and I get minus 0.233. And 3 is repeating forever. You can also use this notation. Part of the education is just coming to lecture and watching these kind of things that you don't always catch in the book. You can write this as minus 0.23 with a bar over it. And the bar means repeat whatever digits are underneath the bar over and over. So this will repeat the 3 forever and ever. Minus 2.3, Revitan 3. There's number 2. Here's our next problem, is to find dw dt by the chain rule if w is this function, x is this function, y is this function, and z is this function of t. So the idea is that w is a function of t alone through these intermediate variables x, y, and z. You might have a parametric curve in the xy plane where you move along that curve, x this function of t, y this function of t, z this function of t. Look pretty strange. You can find the rate at which w is changing in time through these intermediate variables. And I asked you to use the chain rule. I mean the chain rule for functions of multiple variables here. You're not allowed to go plug in x, y, and z and then take the derivative directly, is what the instructions intend. So I want you to do this, write down the chain rule. Here's a helpful thing you can do. You can draw this tree. You don't have to do this part. I'm very happy if you don't do this part, actually. But I like it as an illustration. W is a function of x, y, and z. X, y, and z are in turn functions of t. So what you can do is go through, and on every path from w down, you put a partial derivative. Here's partial of w with respect to x, since I go from w to x. Partial derivative of w with respect to y when I go from w to y. And over here, partial of w with respect to z. Now in each of these paths, I only have one dependent variable, so I write an ordinary derivative. I'll write dx dt, dy dt, dz dt. And now the chain rule says if I want to take the derivative of w, the top variable, with respect to t, the bottom variable, and I take all paths down to t, and in this case all 3 paths go to t, and I multiply the derivatives, partial and ordinary, along each path, and add the paths together. So I'll take dw dt is dw dx, dx dt, the product of the derivatives going along this path, plus dw dy, dy dt, the product of derivatives going along this path, plus dw dz, dz dt, the product of the derivatives going along this path. And if you don't write the tree, then you're just taking all paths down through all the intermediate variables down to t. So you can go through x to t, you can go through y to t, go through z to t. So you can just start here just as easily. All right, now what's dw dx? Here's w. I treat y and z both as constants, and I say derivative of x squared is 2x, and this comes out to be 4x times y squared z cubed. Multiplies dx dt. Well, this is a tricky one here. It's a chain rule itself from ordinary derivatives. Dx dt is, think of this as u is du squared, du is 2u times derivative of u. So what we have here evidently is 8t minus 4. So there's the chain rule from calculus 1 for x equals 2t minus 1 quantity squared. So this must be 8t minus 4. And then dw dy, let's see, dw dy, I treat x and z as constants, so I've got 2y times all the rest of the stuff. I get 4x squared y z cubed. There's dw dy. Y squared being 2y, multiplying the rest of that treated as a constant. Then times dy dt, well, let's see, that's 3t squared. Now dw dz, I treat x and y as a constant, so I have this treated as a constant times 3z squared gives me 6 x squared y squared z squared, all times derivative of z with respect to t, which is minus 1. And there we have the w dz. However, the idea is that w is really a function of only one variable, t, three of these intermediate variables, x, y, and z. So we want to put everything back in terms of t only. So I got 4 times x. Let's see, x is 2t minus 1 squared. Times y squared is t cubed squared is t to the 6th. Times z cubed is 2 minus t cubed. That's 4x squared, y squared, z cubed. All multiplies 18 minus 4. Maybe I should write that as 4 times 2t minus 1. Since I've got a factor of 2t minus 1 already here. Now I come over to 4x squared is 4 2t minus 1 squared. Y is t cubed. Z cubed is 2 minus t cubed. And then all multiplies 3t squared. And then the last part plus 6. X squared is 2t minus 1 squared. Y squared is t to the 6th. And z squared is 2 minus t squared. All multiplies by negative 1, so maybe I just put the minus out front there. And now there it is. I think I'll leave the answer here. This can be multiplied out to find out what the function is. Well, let's see. I do have a 2t minus 1 squared and everything, and a 2 in every factor. So maybe I should pull out, let's see, pull out the twice 2t minus 1 squared that occurs everywhere, and then the first term here I get twice t to the 6 times 2t cubed is 2 minus t cubed. Alright, so 2t to the 6th 2 minus t cubed times let's leave it here. How about, lest I take too long on that. Let's say on the test you don't want to multiply that out unnecessarily. Alright, so there's number 3. There's number 4. Find an appropriate form of the chain rule to find dw, dz du, and dz dv. Show your work. Alright, so 4a. As z equals x squared minus y tangent x, where x in turn is u divided by v, and y is u squared times v squared. This time, I have z written as a function of x and y, and x and y in turn functions of u and v. So I can put partial derivatives on all the paths, but I think it's easier just to remember what they are. And if I want to calculate dz du, then I take all the paths that go down to u, and I multiply the derivatives along those paths, and then add all the paths together. So I've got dz dx going from z here down to x times dx du. These are both partial derivatives because each node goes down to more than one variable. Then I also had to add this path, dz dy, since I go down to y, dy to u. Now let's see, dz dx from here, I treat y as a constant, and I get 2x minus y times derivative of tangent x is secant squared x. So there's dz dx, that multiplies dx du. which is 1 over v, right? It's x times 1 over v is treated as a constant. And then I have to add to that dz dy. Well, let's see, y only occurs here, so this is 0 minus 1 times tangent x. So this is minus tangent x, partial of z with respect to y, times dy du is treating v as a constant, 2u v squared. Now this one I can simplify a little better, so let's try that. I need to put x back in terms of u over v, so this is twice u over v, minus y is u squared v squared, and that multiplies secant squared u over v, all times 1 over v, and then minus 2 tangent x, where x is u over v, times 2 uv squared. So copying it down, sorry I wrote that off the bottom. So I just put in what x and y are. X is u over v, y is u squared v squared. And now let's see if we can simplify this. This looks like 2u over v squared. When I multiply this times this gives me minus u squared v secant squared u over v. This v canceling one of these. And then minus this term is minus 4 u v squared tangent u over v, combining what I can there algebraically. So that's that one. I think I'll leave off the zdv, it's the same kind of thing. Let's look at 4b just quickly. Z is equal to e to the xy, x is equal to uv, and y equals 1 over v. On this one, you can write the tree, z going down, to be functions of x and y. X is a function of u and v, but y is a function of only v, so you can put here dy dv, ordinary derivative. These, however, are partial derivatives. You don't have to write these in. Alright, and I'll say now the chain rule says if I want to calculate dz dv, let's say, that's one of the things we were asked to compute. I have two paths down to v, so I take this path down, multiply its partial derivatives, dz dx, dx dv, and then I have this path down, dz dy, dy dv. Alright, and then dz dx, z is equal to e to the yx, y treated as a constant, remember derivative of e to the kx is k e to the kx, so with y treated as k, this is y e to the yx. So that's dz dx. Then dx dv, if x is u times v, is just u. dz dy, let's see, same thing, it's a constant times y, so it's x e to the xy. And dy dv then, think of this as d to the minus 1, the derivative of v to the minus 1 is minus 1, v to the minus 2. Alright, now I have it, I've just got to put it back in terms of u and v. X is equal to uv and y is 1 over v, so this is 1 over v e to the x times y is apparently u, all times u, plus x is uv e to the xy is 1 as u, and minus 1 over v squared. This one you definitely want to simplify. This is u over v e to the u minus u over v e to the u gives us nothing. All right. The reason that came out to be nothing, here's how can that be? If you think about it, e to the xy is e to the u. And this wasn't a function of v at all, so partial of z with respect to v is 0. How about that? All right. Now, number 5, let's find the slope of the surface in the x direction here. Right? If f of x, y, I guess you can't see it there. There it is. If f of x, y is equal to 4x squared y minus y to the 4th, what's the slope in the x direction at the point square root 3, 1? Slope in the x direction is the partial of f with respect to x. So you treat y as a constant and you get 8xy minus nothing. And if we're going to evaluate it at the point square root 3, 1, this just becomes 8 square root 3. Right? Now, a little trickier. Suppose I try 5c. Suppose I want the slope in the direction of the origin from. So let's say slope in the direction of the origin 0, 0 from the point square root 3, 1. What if you move in that direction? When you're not moving in the x or y direction, it's the directional derivative. And actually, the directional derivative is the partial derivative in the x and y directions when you're moving in those directions. So we want to move towards the origin 0, 0 from square root 3, 1, with the direction is minus square root 3 minus 1. And again, for points coordinates, I'll use round brackets. For a vector, I use angle brackets. This will be the direction. And now to calculate the directional derivative, I need a unit vector in that direction. So I'll just take v divided by its length. So this is the vector minus square root 3 minus 1 divided by the root sum square of those same components. Well, the root sum square of these is equal to 2. So that's my unit vector towards the origin is minus square root 3 over 2 minus a half. Oh, I keep trying to connect these. Alright, I'm sorry with that off the bottom. There it is. The direction of the origin is minus square root 3 minus 1. When I'm coming from square root 3, 1. And I divide that by its length 2 to get the unit vector. Now, I also need the gradient to calculate the directional derivative. So the gradient of f I'm interested in at this point also, square root 3, 1. That's the point at which I want to calculate the slope of the tangent line. Well, the gradient is the vector of partial derivatives with respect to x and y. If you look back at the function up here, partial with respect to x was 8xy. Partial with respect to y is 4x squared minus 4y cubed, right? So we'll bring that down here. Here's the partial, and then I have to plug in the point square root 3, 1. I want the slope in that direction. So this is 8 square root 3, 1 is 8 square root 3, and then I plug in square root 3, 1, I get 12 minus 4 is 8. So there is the gradient at square root 3, 1. Here's the direction, minus square root 3 over 2 minus a half. The directional derivative at the point square root 3, 1 in the direction of u towards the origin is the dot product, gradient of f at the point dot u is 8 square root 3, 8 dot square root 3 over 2 minus square root 3 over 2 minus a half. And let's see. We've got 8 times 3 over 2 gives 12. Minus 4. Apparently, is that right? 3 times 8 is 24. Divided by
2 gives 12, and then minus 4 gives 8 for the directional derivative then. D is kind of interesting. D says find the largest directional derivative and a unit vector in that direction at square root 3, 1. So the largest directional derivative is always the length of the gradient at that point, but we already calculated that. We found out the gradient was 8 square root 3, 8. And there's a little trick here you can use if you want. If a vector is multiplied through by a number, you can pull its absolute value out. Remember, if you have a scalar times a vector, the length of the new vector is the absolute value of the scalar times the length of the vector that's left. So we can pull the 8 out and write it as 8 times the length of square root 3, 1. So this is 8 times square root of square root 3 squared plus 1 squared. You don't need to take this much time. This is 2. Apparently, the length of the gradient is 16. That's also the largest directional derivative. What's the direction? The direction is the direction of the gradient. So this is the significance of the gradient. It points in the direction of greatest increasing slope, and that slope is the length of the gradient. So the direction, you could just say it's the length of the gradient, it's the gradient, but if we want a unit vector in that direction, we'll say it's the gradient divided by its length. The gradient was 8 square root 3, 8. Its length was 16, evidently. The direction is the unit vector square root 3 over 2, 1/2. Oops, there we go. So apparently the first vector we got was actually pointed in minus the direction of the gradient, and we were getting the minimum possible directional derivative as a result. All right, here's number 7. Suppose I want to find a unit normal to the level surface, w equals 10, of this function, w equals 2x squared plus 4y squared plus 4z squared, at the point 1, 1, 1. And what you're noticing here, I could leave part of this out. I could just leave out the w equals 10. Because if you put in 1, 1, 1, you get 2 plus 4 is 10. But the idea is there's a level surface through this point. What is the normal vector to it? What is this here if you think about it, a level surface? 10 equals this. You can divide through by 10 to put it in standard form and recognize this is an ellipsoid. So I'm finding the normal vector to the ellipsoid. All this stuff equals 10. That's a level surface of this 4-dimensional object here, w written as a function of x, y, and z. All right. So what we have can be done 2 ways, actually. I think the easiest way is to say that the gradient of f of w is normal to the level surface through the given point. 1, 1, 1, where in this case we want w equals 2x squared plus 4y squared plus 4z squared. All right. Zoom this out just a bit. So the gradient of w then is the partial with respect to each of the variables. Partial of 2x squared with respect to x, or partial with respect to x is 4x plus 0 plus 0. Partial with respect to y is 0 plus 8y plus 0. Partial with respect to z is then 0 plus 0 plus 8z. So there's the gradient, and if I take the gradient of w at the point 1, 1, 1, I get the vector 4, 8, 8. So there's a normal to the surface we just need a unit normal. So n, the unit normal, is this vector 4, 8, 8 divided by its length. And I want to show you a little trick. This is one of the things you get by listening to the lectures, is some things that will maybe save you some time in the workplace. You know what's easier than doing this? These are kind of big numbers. Another vector that points in the same direction is the vector 1, 2, 2. If I take a unit vector in that direction, it will be the same unit vector. So I could take 1, 2, 2 over square root 1 squared plus 2 squared plus 2 squared. Well, this is square root 9, that's just 3, right? So this is the vector 1/3, 2/3, 2/3. That is the unit normal, a unit normal, to the level surface of this function for variables. What's another unit normal? Turns out there's two of them. Another possible answer that's just as good, right, is to take the vector in the opposite direction is also perpendicular to the surface. It's just one is an outward normal to the ellipsoid, and one of them is an inward unit normal to the ellipsoid. So either one of these answers is a good answer. All right, how about this one? If I look at number 8, what is an equation of the tangent plane to z equals x to the 7th over 2y squared at the point of tangency 2, 4, 4. How about that? Here's what you think when you want a plane. You want a unit normal to the plane, and you want a point on the plane. I already have a point. It's given. So all I need is the unit normal. What is the unit normal here? One thing you could do, you could write this as w is a function of x, y, and z, and do a unit normal to the level surface through the point, as we did in the last example. I think that's unnecessarily complicated. An easier thing to do is if you can just memorize that the unit upward normal to any surface z is a function of x and y. We'll call it f of x, y. This is a formula, is you take minus df dx minus df dy and 1. This actually comes from subtracting this f over to this side and rewriting it as z minus x to the 7th over 2y squared equals 0, and say this is the level surface w equals 0 of w equals z minus x squared over 2y squared. That's actually how we derive this formula here. So if you think of this as a level surface like in the last example, then this would be, you could compute this unit normal from that. But I like to memorize this one and say a unit normal to the surface c written as a function of x and y is minus df dx minus df dy. 1 I'm sorry, that's not a unit normal, that's a normal. Sorry. And so this is a normal, let's see, df dx, treating y as a constant, is just 7x to the 6th over 2y squared. Alright, treat this as x to the 7th times a constant, and then I need a minus. Minus df dy, take minus, so don't forget it. Treat this as x to the 7th over 2 times y to the minus 2, and the derivative is minus 2, y to the minus 3, times x to the 7th over 2, and then 1. And I want the unit normal at this point. Let's see, 2, 4, 4 it was. So this is at the point 2, 4, 4. So I just plug in, actually 2 for x and 4 for y, and I'll wind up with minus 7 times 2 to the 6th over 2 times y squared. Well, y is 4, and 4 squared is 2 to the 4th, so I'll write it like that. And then minus 2 the 2 and the 1/2 cancel, so we get minus y to the minus 3 will be 1 over 4 cubed, or 1 over 2 to the 6th, and x to the 7th is 2 to the 7th, and then I have 1. So I've done a little bit of fast powers of 2 here. Now let's see, 2 to the 6th over 2 to the 5th is 2, so this, oops, this minus went right here. So that leaves minus 14 for the first component. And then 2 to the 7th over 2 to the 6th is again 2, so I get minus 2 here and 1. There is a normal, and we don't care if it's a unit normal or not. Actually, we just need any normal to the tangent plane. Given the normal, if we call those components A, B, and C, at any point we'll call those coordinates up here. Zoom out just a bit. The coordinates of the point are x0, y0, z0. Remember the point normal form of a plane? It's A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. When you have a normal with components a, b, c, a point with coordinates x0, y0, z0, you just plug those numbers in, and I get minus 14 times x minus 2 plus minus 2 times y minus a negative 2. Oops, let's see. Y minus 4 plus 1 times z minus 4, all equals 0. You want to simplify this, not leave it like this. Put it into standard form, ax plus by plus cz plus d equals 0, or ax plus by plus cz equals d, depending on the book you take. This is apparently minus 14x minus 2y plus z, and then I've got 28 plus 8 is 36, minus 4 is 32, and I'll carry that over to the other side as minus 32, and there's a good equation for the plane.
These problems with absolute extreme are actually rather difficult, but the concept is very easy. The idea is in calculus 1, remember if you had a function of one variable, you could draw it as a curve in the plane. To find an absolute maximum, absolute minimum of a continuous curve over a closed interval, you just plugged in the endpoints and you plugged in the critical points, and whichever was the largest was the max, whichever was the smallest was the min. This is very similar in concept. Now f of x, y is a surface, and if you have a continuous surface, like this is a polynomial in two variables, over a closed bounded region, then all you had to do was plug in the interior critical points and plug in the critical points along the boundary, and the largest is the maximum and the largest is the minimum. The boundary you have to write as a curve function of one variable and use calculus 1 to find its critical points. But for the interior, you need to find the critical points of the function of two variables. And here's what we can do. Suppose we want to find the absolute extreme of x squared plus 2y squared minus x over the unit disk. X squared plus y, not unit disk, the disk of radius 2, x squared plus y squared less than or equal to 4. This, interestingly, if you think about it, you can kind of get an intuition for what to expect in the answer on this if you think about it. What kind of curve is this? If you complete the square in x, you'll find out this is actually an elliptic paraboloid. You can write this as z equals x minus a half quantity squared plus 2y squared plus, I guess, minus a quarter. And you'll see that this is the form of an elliptic paraboloid that's just got its vertex shifted away from the origin. And so it's moved over a little bit from the origin and setting over the disk about the origin. What do you expect for the high point and low points? You can get this kind of intuition, and you don't have to do this part. But it's moved over to x equals 1/2, so this is 1/2, 0, 0. And at this point, you have an elliptic paraboloid coming up like this. And you say, what's this maximum minimum value over the disk of radius 2? Well, you're going to you can think of the
image of this up on the side of the parabola, elliptic paraboloid, and think, what's the highest point? Well, it's probably on this side where you get up to the peak, and what's the lowest point? It's probably on the sides where you get down to the middle. So you might get two minima here and one maxima here. Let's see if it comes out that way or not. That's just intuition looking at it, but sometimes that can be really helpful. Immediately what you observe is that there is a maximum and minimum because it's a nice smooth surface over a closed bounded region, right? So you know that from the theorem. Now how do you find this? You find first the interior critical points. For a function of two variables, you set both partial derivatives equal to 0. So you set 0 equals fx, which is, let's see, 2x minus 1. And you also set 0 equals fy, which is 4y. So both those have to be 0. This one tells you that x equals a half. This one tells you that y equals 0. So there's only one interior critical point. It's at the point x. Oh, I was looking at this. Actually, the minimum is down at the bottom here, isn't it? And that's what we just found. X is a half, and y is 0 is at the bottom of the elliptic paraboloid. So there's one interior critical point, and x equals a half, y equals 0. And then we need to check the boundary. The boundary can be rather difficult, unfortunately, but at least it's calculus 1 in the end. So how do we check the boundary? What you can do is say, well, the boundary is a circle. Let's go around this circle, say beginning from the point 2, I guess this one, 2, 0, 0. Let's go around the circle. We can use that, the parametric equations, x equals 2 cosine t, y equals 2 sine t, because after all that goes around a circle of radius 2, which is the boundary of this disk, right? Now, along that boundary, z, or f of x, y, is f of x of t, y of t. You're sweeping out a curve in three space here, x, y, z, and f was 2x squared, so this is f of 2 cosine t, 2 sine t, where f was x squared, would be 2 cosine t squared, plus 2y squared is twice 2 sine squared, and then minus x is minus cosine t. So there is, along the boundary, the function of t. And now to sweep out the circle once, we'll say 0 is less than or equal to t is less than or equal to 2 pi. And so now we have a function of one variable. You can think of this as z of t traverses this path, a function of one variable. You want to maximize along the boundary. You find its critical points. You set dz dt equal to 0. But dz dt, according to this, well, let's simplify it a little. This is 4 cosine squared t plus 8 sine squared t minus cosine t, and its derivative by the chain rule is 4 times minus 2 sine t. I'm sorry, 4 times 2 cosine t times minus sine t by the chain rule for this first term. For the second term, we've got plus 8 times 2 sine t cosine t. And for the last term, it's minus sine, plus sine t. Derivative of cosine is minus the sine. Evidently, this is 8 times minus 8 times sine cosine, plus 16 times sine cosine is 8 sine cosine. And all add to that sine t. So we need this equal to 0 for the critical points along the boundary. Well, how do you do that? You could factor out a sine t, and this is 0 equals sine t times 8 cosine t plus 1. Alright? evidently either sine t equals 0 or cosine t equals minus an eighth. So there's the following points we need to check: t equals 0, or t equals pi, or t equals 2 pi, but that's back at the same point, 2, 0, 0 here. We go around, we can say t between 0 and bigger than or equal to 0 and less than 2 pi, and sweep out all the points once. So we're checking those 2 points, and we're also checking t equals the inverse cosine of minus an eighth. And also, if you think about it, there's 2 points in the circle where cosine t is equal to minus an eighth. You can also take 2 pi minus the arc cosine of minus an eighth. All right. Now, those are, let's see. Right, okay. So now we've got to check all those, and we just plug them in to the equation, the function, because we know, so let's just recap. 1, we find the interior critical points. 2, we found the boundary critical points using calculus 1. And now we just plug in each point. This one corresponds, when t equals 0, to x equals 2 cosine 0, y equals 2 sine 0 is the point 2, 0. Pi corresponds to x equals 0 and y equals 2 sine pi. Let's see, sorry. So this is 2 times cosine pi is minus 2. And sine pi is 0. So there's those 2 points for 0 and pi, and then for arc cosine of minus an eighth, you get 2 cosine of arc cosine of minus an eighth is minus an eighth, and the sine of the arc cosine of minus an eighth. And then you have the one more point, 2 pi minus that, gives the same cosine and minus the sine, so we got minus an eighth sine, plus an eighth. Let's see. Cosine should be the same, and the sine, so you take the sine of the arc cosine. Anyway, you plug in the 4 points. I'm trying to do too much of this in my head here. Plug in the 4 points, and what you find out actually is that the high point is going to occur at the back of the disk, where x is minus 2 and y is 0. So you just plug all these in and take f of 2, 0 equals f of minus 2, 0 equals f of minus an eighth sine of the arc cosine of minus an eighth. And this actually reduces to an algebraic expression using trigonometry, the sine of the arc cosine. And then you need f at the interior and f at the other point. Minus an eighth sine of the arc cosine of 2 pi sine of 2 pi minus the arc cosine of minus an eighth, and take f of the interior critical point 1/2, 0. This one, if you plug it in, comes out to be, let's see, 1/2 squared, that's x squared, plus 2y squared is 2 times 0 squared, minus x is minus 1/2, comes out, looks like to be minus 1/4. And then that's the minimum, turns out. That's the smallest value you get out of this. And the maximum, I believe, comes out at minus 2, 0. We plug that in, we get minus 2 squared plus 2 times 0 squared minus a minus 2 comes out to be 4. Minus 2, plus 2 is 6. That should be the highest point. So you can plug these others in and check, but I think this will come out to be the max, and this one will come out to be the min. This time, instead of finding an absolute max and an absolute min over a closed bounded region, we're going to try and find relative maxima and minima, right, of a function, and we don't need a bounded region anymore. How do we find the relative maxima and minima? Again, it's similar to calculus 1. You find the critical points and you check each one with the second derivative test is what we'll do. So, step 1, we find the critical point. The critical points of a function of two variables are where both partial derivatives are 0 or don't exist. And since this is a function that's differentiable everywhere, there is no place where they don't exist, so it suffices just to set the partial derivatives equal to 0. Where they're both 0, we'll have a critical point. So, partial with respect to x of this function is 3x squared y plus 24x. Partial with respect to y is x cubed minus 8. How do we solve that? In general, there is no nice method for solving a system of nonlinear equations like this. It's just by hook or by crook, by whatever algebra you had before and whatever other tricks you know. Well, I remember from algebra that this one, x cubed minus 8 equals 0, is it factors like this. X cubed minus 8 factors as x minus 2 times x squared plus 2x plus 4. By the formula for factoring, it looks like this. A cubed minus b cubed factors as a minus b times a squared plus ab plus b squared. So I use that formula to do this factoring here. From which we conclude this isn't factored anymore because it doesn't factor anymore. There are no solutions to this factor equals 0. It's what we call an irreducible quadratic. Right? If this is an ax squared plus bx plus c, b squared minus 4ac is negative, means that this doesn't factor using real numbers. So the only solution here over real numbers is x equals 2. There are complex numbers that satisfy that we're not interested in, right? Since this is a real problem. So the second one says that in order for the partial with respect to y to be 0, we have to have x equals 2. Now we plug that into the first expression and say, well, if x equals 2, this becomes 3 times 2 squared is 12. Y plus 24 times 2 is 48 equals 0. Evidently, y equals negative 4, and there's only one critical point. That's x equals 2, y equals minus 4. That's the only candidate for relative max, min, and saddle points. So on step 2, we test each critical point, we only have one, by the second derivative test. Because in this calculus, we don't have a first derivative test. It's complicated, and you can do it on an ad hoc basis for various functions, and we'll just use the second derivative test. For the second derivative test, I'm going to need the second derivative, so I compute f(x)(x), the second derivative with respect to x. I have the first derivative, so I'll just take one more derivative, and I get 6xy plus 24. Then I need fyy. I can take partial of y with respect to y, and I get 0. And then I need the mixed partial, fxy. So I'll take either partial of fx with respect to y or partial of fy with respect to x, because remember, the mixed partials in either order give you the same result for a function that's twice differentiable in the neighborhood of the point we're at, which is everywhere here. So fxy, let's do the easy one, take partial of fy with respect to x. So to compute fxy, we'll instead compute fyx, they're equal, and take this partial with respect to x as 3x squared. Now what we have is to compute d is fxx, you just have to memorize this or look it up in your open book test, fxx fyy minus fxy or fyx squared is, well, fyy is 0, so this is 0, minus fxy squared is 9x to the 4th. Now, at this point, d at the point is equal to minus 9 times 2 to the 4th. We don't care what that is, it's just less than 0 is all we need to know. Less than 0 makes it a saddle point at 2 minus 4. Since there's no more critical points, there can't be a max or min, so there is no relative min or relative max. Finally, let's try problem number 11. Show that the limit does not exist. Remember, we did limits a long time ago. You could show that they do exist at certain points. For instance, this is a continuous function of x and y within its domain, which is everywhere. This is a continuous function of x and y within its domain, which is everywhere. Because a polynomial in two variables is continuous everywhere. The square root function of any positive number is continuous. You have to worry about at 0, 0, where you get a division by 0 here. This is not continuous, and so this quotient is continuous everywhere except at the point 0, 0. And what that means is that if we'd ask for a limit at any other point in the plane, right, we just plug the numbers in since it's continuous. Continuous means you can plug the numbers in to get the limit, right? It means the value of the function is equal to the value of the limit. But I give you, of course, the one hard point, right? So what is the limit there? Does it exist? Well, I gave you a hint, it doesn't exist on this particular function. Here's how you can show a limit doesn't exist. Is you can try approaching the point from different paths. If the limit really exists, you have to be able to approach from these different paths. The limit along each path to the point, the origin in this case, has to exist, and all the different limits have to be the same, from coming from any direction you want, along any path you want. So we'll say, let's look at this path. Along path C1, let x equal t and y equal 0. Let t go to 0 from the right. This limit should be equal to some number, it looks like, since it's close to polynomials. If it doesn't exist, we're done. If a limit from any direction doesn't exist, we're done. What do we get? We get 0. I want to point out what is going on here, too. It's worth drawing. What did we do here by saying x equals t, y equals 0? In the xy plane, we're approaching along this path. X equals t, y equals 0, t going to 0 from the right. This is our curve, C1. We're approaching the origin, the point at which we want the limit of the function, like that. And we're finding out that the limit is, well, if we rewrite this with x equals t, this will be the limit as t goes to 0 from the right of t times 0, since x equals t and y equals 0, over square root t to the 4th plus 0 squared, which is the limit as t goes to 0 from the right of, well, the top 0 always for any t, 0 over t squared. the limit of 0 over anything is equal to 0. That's how I got evaluated this limit here. Now for the second one, suppose I go along curve C2. Curve C2, what is that? I'm letting x equals t and y equals t. Now that's, if you substitute in, this is the line y equals x. So x equals t, y equals t is the parametric equations for the line y equals x. I'll let t go to 0 from the right again, so I'm coming in like this. Let's draw it. Suppose I approach the origin this way, along this path. There's C2. Now what do I get? Let's write it down here. I've got some space. If I put in t for x and t for y, then this becomes the limit. T approaches 0 from the right of t times t is t squared over square root t to the 4th plus t to the 4th. Well, let's see, that's limit. T goes to 0 from the right of t squared over square root of t squared, square root of 2 times t squared. The t squareds cancel, and I got limit 1 over square root 2 is 1 over square root 2. Let's see. This isn't right the way I've got it written up. This should have been t to the 4th. And this is square root 2t squared. And so the limit is 1 over square root 2. And since these two limits are not the same, right? This limit was 0, and this limit was 1 over square root 2. We infer that the limit as a function of two variables doesn't exist.